Morning, Lonnie.
Good morning.
Good morning. All right, so you are here. Did you get a chance to read about kilonovas?
Yep, I sure did.
Okay, cool. They're pretty interesting, huh?
Colliding neutron stars?
Colliding, yeah, merging neutron stars, right? And this is the first one that we'd ever seen, so it's kind of an exciting thing. We hope that it's going to be just the beginning of a new era. So that's actually one of the exciting parts that you guys are going to see happen, right? Over the next few years, the gravitational observatories are going to detect more and more of these events. So we're going to start to understand a lot better, like how the universe looks the way it does, really. So, yeah. Good morning. Oh, my three amigos. You guys are always here. Thank you for being here so consistently. So we just have a few more days to talk, and actually one of the things that you guys want to talk about maybe is what are we going to do with the final? So your final is scheduled for Monday, but I think what I'm going to do is I'll open it on Monday and then I'll actually give you a couple of days. But I will make it a time test. So I don't want to give you more than 2 hours worth of content. So I'll give you a little more time than that, but really please, the goal is to try to get it done in under 2 hours. So I will test it myself and make sure that I can do it in a reasonably short amount of time. And then you guys will go ahead and take that test. But I'll give you until, I think I'll open it on Monday morning, and then you can take it anytime on Monday or Tuesday. So any suggestions? Anything you guys want to see on the final? Any topics that you'd like to see on the final? What's your favorite topic since the midterm?
Is the final cumulative?
One more time?
Is the final cumulative?
You're supposed to be aware of the previous stuff, but I probably won't be doing a lot of calculations, right? Because we haven't done a lot of calculations. So it's going to be a lot less than the midterm. Okay. So more focus on the last stuff, but you shouldn't forget the previous stuff, right?
Yeah.
Okay, so yeah, it's more focused on the later stuff. Okay, all right, so we'll wait a couple more minutes, and then I think you guys are kind of my main crew. I have a couple people watching on YouTube, so hopefully the rest of the people will do that too. Okay, I'm gonna go ahead and pin my video again. Oops, spotlight it? I don't know, what's the difference between everybody sees this as big? That's what happens, okay. All right, so let me talk to you guys. So good morning and welcome back. And so we just have a couple more classes. I have way too much stuff to put into 2 classes, so I have to limit myself. I have some ideas like what I'd like to cover, but I'm okay with not covering everything that I want to cover. And if you guys have an interest, if there's something that you find particularly interesting you'd rather talk about, I'm okay with that too. There's just the 3 of you guys, so actually you have a really important influence right now if you're interested in making the class go one. Hey, there's Brandon. Okay, if you want to make the class go one way or the other. But I do have some things I want to talk about today. So I definitely want to tell you guys about or not tell you, but talk about the kilonova event. This was an extraordinary event, and to live through it was just, I mean, you all lived through it, but you didn't realize maybe the magnitude of what was happening. But it was a pretty exciting event, and we were kind of given a front row seat because we are friends with some of the people who discovered it. And the video that you watched, the first kilonova, was produced by the Las Cumbres Observatory. out in Galita, and they have a worldwide network of telescopes that was able to watch the kilonova better than any other group in the world, which is kind of exciting. You know, we're right next door. And then one of the researchers for the project, actually the one who created the program that would quickly be able to search for the kilonova event, came and gave us a talk actually on the kilonova. So that was pretty exciting. His name is Yair Arkabi. And anyways, so this is a really fun, exciting event. And then, you know, what is it all about? So hopefully you all watched the video, you took your little quiz, so you heard some of the big detail. But the exciting thing is that we had never seen one of these events before. You should know that, right? The kilonova, the kilo stands for 1,000 times the intensity of a nova. It's 1,000 times of a nova strength. So literally kilonova, right? About 1,000 times the energy output of a nova. So what's a nova? Does everybody know what a nova is? I think you know, but maybe not. Actually, maybe not. Anybody know what a nova is?
I think just a nova is when there's like a binary star system.
Uh-huh.
Star dust poofs off of a bigger star and falls onto its companion. It fuses on contact because the different.
That's right. Very good. Okay, so a nova is occurring generally with a red giant white dwarf pair, but actually it doesn't have to be, it turns out. There are probably many variations on this, but what happens is that the outer layers of the red giant are actually probably being released. I mean, they are being released in shells of material. And at some point, those shells are going to get too far away from the red giant and are actually going to be captured by the white dwarf. But they don't just go straight in, by the way, they go into a kind of orbit, an accretion disk around the white dwarf, and then eventually land on the white dwarf. Okay, and they are, as Lonnie said, instantly fused, and then you know, the white dwarf gains a little bit of mass. So these are called what are they called? Symbiotic binaries. Symbiotic binaries. That's actually going to be true no matter what. A symbiotic binary means there's a mass transfer from one of the members to the other one, accompanied by a flash of light. This is a temporary thing, right? Just a brief flash of energy that occurs from the output of the fusion of the material that landed on the white dwarf, for example. And then it goes, you know, kind of goes back to normal again. So, but this keeps happening year after year, and then can eventually lead, and so I think we must have talked about this, right? We talked about an exploding white dwarf, right? An exploding white dwarf is called a type 1A supernova. Okay. And the reason it explodes is it goes above the Chandrasekhar limit, which is 1.4 solar masses, right? It's called the Chandrasekhar limit. Okay, so, but anyways, that's a nova, right? A nova occurs year after year and then may lead to this, not always, but a kilonova is something incredibly different. 1,000 times the energy output, but it is a very fast event. It's kind of unbelievably fast. And I think this is probably the reason why, so I'm gonna ask the question, why haven't, I just answered the question, why haven't we seen a kilonova before 8/17/2017, right? So that one's easy to remember because it's August 17th, 2017, okay? So the question is, why haven't we seen a kilonova before? So I'm gonna put an E on there, before 8/17/2017, and the answer is It is called a transient event. What is a transient event? Anybody figure that one out? Transient. I got 4 people here. Here you go. What do you got? Lonnie, I saw you unmute. Come on, tell me what a transient event is.
I keep thinking of like when the stars transit in front of each other, so I'm not too sure.
Okay, that was a good guess, actually. So a transit event is a temporary obscuring of one body by another. That's not the same word. Transit is good. It's close, but it's not a transient event.
It's like an impulse almost. It's like it's the opposite of steady state.
Okay, that was a good guess too, actually. So it's close enough. I think what we were going to look for is it's very temporary. So it doesn't last long. Does not last long, right? The very bright part of it lasted actually, okay, so I don't want to just tell you. Did you already know? Anybody know how long it lasted? How long did this last, kilonova? It happened 3 years ago, right? How long did it last? Anybody? What I guess? Just guess. Just guess.
A couple of days.
Okay, that's a good guess. Actually, so the brightest part of it only lasted about 4 or 5 days. But actually, I'm tricking you a little bit because we can still see it now. Okay, so in fact, if you know where to look, the after effect of the kilonova, the expanding cloud, and what was left behind is still visible. But you have to know exactly where to look. But the kilonova event itself only lasted as a bright, thing in the sky for about 4 days. So if you didn't look very carefully, you would have missed it, right? It was just over. Okay, so let's take a look at. Actually, I feel like maybe we should just do a quick. You saw the video already, though, so you already saw the LCO video. But let me just put kilonova 2017 kilonova. Okay, so this is let's look at the light curve. Okay, let's see if we can find a light curve. Okay, so actually I should show you guys what I'm doing so that you can do this yourself. Okay, so okay, so I just typed in kilonova 2017 light curve. Okay, and I'm getting some different things. This is the actually, I don't know, I'm not sure which one it is. Here's what you want to know though. That one event, oh, here we go. This is actually what we want. LCO light curve, because they got the best version of it, right? They have the most complete light curve. Okay, so what you want to understand is that it happened in days, right? This is amazing. This is the reason why we've never seen one before. Because if you're not watching, you just miss it. It's gone. And this is the extraordinary part, that they were able to see the peak of the light, right? So now, what does this mean? I don't actually know. Optical emission. Okay, what does optical mean? Visible light. What is this? Well, I don't know what this is. I don't know. What's green? What's blue? What's orange? Hold on. PowerPoint slide. Source data. Okay, that could help. Source data. Okay, so these are the guys. This guy came and gave us a talk. This guy used to teach for us in the astronomy lab. I love it. It's great. Okay, I can't see it. Okay, I can't see the paper. Okay, PowerPoint slide. Let's take a look at that. We download it. Oh, beautiful. That's what I'm talking about. Okay, so optical emission. So this is visible light from a kilonova following a gravitational wave detected neutron star merger. Wow, it's so clean. It tells you exactly what's going on. Okay, so let's just read. So the abstract is supposed to be the real lowdown on the paper, right? The merger of blah, 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 lasting a few days. So it's an optical infrared transient. Okay, so you want to understand what that is actually saying, right? In the optical and infrared part of the spectrum, this only lasts a few days, right? So this is why it's been so difficult to see. But it is still emitting light, and we can still actually watch it, but just not, I'm surprised that it's not infrared too. I would have expected infrared, but it looks like maybe it's going to be something else. We'll see what happens. I don't know the answer actually. Powered by a radio, blah, blah, blah. Okay, Kilo, powered by a radioactive decay of neutron-rich species synthesized in the merger. Radioactive decay of neutron-rich species synthesized in the merger. So you take a neutron star and you smash it together with a neutron star. Are there a lot of neutrons there? Of course. And some of them are going to be ejected in a very violent stream and can then be captured by atoms. And as they absorb the neutrons, they become more and more massive elements. So when you try to understand why this is going to be so important, you want to understand there's a mechanism for feeding neutrons very quickly to a nucleus and allowing them to accumulate. All right. So blah, blah, blah. Okay. A small amount of mass, 10 to the minus 4, 10 to the minus 2 solar masses with low electron fraction is ejected at high velocity, 0.1 to 0.3 times the speed of light, or carried out by winds from an accretion disk formed around the newly merged object. This mass is expected to undergo rapid neutron capture called the R process. We're going to talk about that in just a minute. Nucleosynthesis, leading to the formation of radioactive elements that release energy as they decay, powering an electromagnetic transient. A large uncertainty in the composition of the blah, 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 blah. Okay. Afterglows of gamma ray bursts near infrared. Okay. 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 So, yeah, this is a technical paper. But actually, this is a really cool story. And if you weren't paying attention, this is the story that makes it so remarkable. And I'll find some reason to ask you questions about this on your final. The original detection of this gravitational wave was actually at the same moment that a satellite in space, the Swift telescope, measured a gamma ray burst. And so you want to take a look right here. There is a gamma ray burst and a gravitational wave on the same date and actually at the same time. And because it's such an impossible thing for them to happen at the same time, they concluded it must be from the same event. And so this original target right here is the location that the gamma ray burst came from, right? I think, let's see, the contours indicated 1 sigma, 2 sigma, 3 sigma, right? So these are sigma, remember, is the spread of the probability. So 1 sigma, 67% chance that it's here, 95%, 99% probability within this ring right here. The contours, okay. So then this part is the, oh, these are the gravitational wave boundaries. So that actually is smaller than the gamma ray burst detection. And so Yair, actually the guy who's the lead author here, had programmed the telescope to search through likely galaxies, and they knew the location very precisely, and they had the telescope go and check each one of these galaxies in the region. And just by coincidence, it was the 6th one, I believe, in the list. So they very quickly got to start watching the data. And what's really amazing, like I said, is that they saw the beginning, and then they saw the peak. That's the most important part, it turns out, theoretically, in order to fit your data. This doesn't really look very good, though, does it? Would you guys say this looks very good? I don't know. I got to be a little critical here. This blue line does not really look like this blue line. Seriously. I mean, okay, I'm not going to say anything. They published this paper already, but the rest of the data I'm okay with. Yeah, that looks excellent. This looks okay. It's a little tweaked, This is just the wrong model. Can you guys see this? I mean, I'm not a specialist in this, but you can look at the data and you can see they're making it work because it's the best model they have. Okay, so let's see, what does it mean? Okay, our rapid response, high cadence follow-up constrains the peak of the light curve to approximately 1 day after the merger. Blah, blah, blah. Okay, I still don't know what this means. Oh, these are different models, I guess, huh? Numerical radioactive for ejecta mass and dashed line. Okay, so they're modeling different masses of ejecta. And then the error bars, data from the, okay, well, I still don't know. I'm reading it. Anybody figure this out? Why do they have different colors? I think these are different models. That's all I can think of. That's all I can think of. I have to ask him. I should have asked him before now. But anyways, there you go. That's cool. Excellent. Blah, blah, blah. Okay, so I love that this science has happened so quickly. This is neat. And so anyways, all right, so we saw it and you can see, look, 5 days later, it's already way down here. This is the apparent magnitude. And the higher the number on the apparent magnitude, the dimmer it appears, okay? So, okay, so the answer is it's a transient event. It only lasts for a little while. So you have to get it right away or else you're gonna miss it entirely. And so there was kind of a fortuitous detection simultaneously of a gamma ray burst and the gravitational wave at the same time that allowed them to localize or find a part of the sky to search for. And if you heard in the video, it's only now that the technology exists to start doing an automatic search of the likely areas. So before this year, before a couple of years ago, sorry, before this recent observation, the technology just didn't exist. And now we have it. So what would you expect? We're going to see more of these, right? And actually, so behind the scenes, you should be aware that there are detections of gravitational waves nearly every day now. I know, it's overwhelming. You should know that though. And not all of them are being published because you have to follow up with some kind of observation and then write it up. So they're not all being published. They'll probably be published in a cumulative kind of package from now on because they're happening so frequently. But they have been publishing certain strange ones, right? So you can hear about these strange ones. In fact, we'll talk about one of those today. All right, so what do you need to know? I told you to start looking at the stellar nucleosynthesis. Let's go ahead and take a look at that real quick. Not real quick, we're gonna spend a little time on this. This is important. So stellar nucleosynthesis means nucleus building inside of stars, but it's really actually not just inside of stars. These are the processes that are happening in stars. If you're interested, we can talk about the details here. One is called the PP chain, the other is the CNO, and there's a triple alpha. These are all common processes. And then we have, these are living stars, right? In living stars. So this is an interesting article, by the way. This is a very interesting article. Actually, I thought this was, we've talked about, oh, maybe we never did talk about this actually. Remember, I don't know if you guys remember reading in Hawking's book that there was a paper with, what's his name, Alpha, Beta, Hans Bethe, and anybody know the other name? Hans Bethe and blank. And then they talked George Gamow into being on the paper so that the three authors were Alpha, Beta, Gamma, ABC. So anyways, you don't need to worry about that. So Bethe, where's the Atkinson maybe? No, it's not Atkinson, somebody else. All right, well, let's just jump down to the key thing right here. Take a look at this periodic table. So this is what I want to talk about with you guys for a little while. So you should know a few things, right? Number one, we've already talked about this, but if you look, what did the Big Bang produce, right? The Big Bang produced hydrogen and helium, and it turns out a little bit of lithium. Do you see any more blue? No, there's no more blue. Only the simplest elements could be created in this process. So I have to be honest, up until a few years ago when this came out, I was a little ignorant personally. I just did not understand. I thought personally that most of the elements came through supernova explosions. I mean, they were either created in a star or they were created in the explosion. And you'll understand in a few minutes why I believe that, because actually that was what we had seen. But the process of exploding leads to the generation of high energy neutrons or other particles, which can then create new radioactive elements from them. But we can take a look right here and see the different things right here. So we've got the Big Bang. We've got a dying low mass star, which is actually like our sun. So our sun, in the last stages of its life, is actually going to blow off shell after shell of its material, of its outer layers, because it's going to be a red giant. You probably know that the Earth will be inside of the sun at that point. And then it's going to blow those shells off. And then at the very end, the core of the star will collapse and form a white dwarf. Now, because the sun doesn't have any companions, it will just stay as a white dwarf, but it's just incredibly hot. And so it has an ultraviolet, it'll shine with the ultraviolet light actually, and other kinds of light as well. It'll be very bright and will energize that cloud, but the wind and the escaping cloud are going to generate elements in the process. So this green stuff is things that can be made by this dying low mass star, like our sun. So now what about an exploding white dwarf? Well, actually a bunch of other elements. So this is what I just talked about, the type 1a supernova. Type 1a supernova, a bunch of elements. And then we have exploding massive stars. So that's a little bit different. And I think maybe I talked about that, right? That you get this kind of a picture where you have an iron core, and then you have layer after layer, which is actually currently fusing, and even an outer layer of hydrogen and helium that may or may not be fusing. And then what happens is when it gets to iron, something special happens. The iron fuses and doesn't release any energy, or not enough at least to power the star. And so the star collapses. Actually, it really doesn't release energy at all. So it turns out the star begins to cool. And so a fraction of a second after beginning to fuse iron, this core will collapse. And from that core collapse, we said there's two possibilities. Either you get a neutron star or you get a black hole. Okay, so these are type 2 supernovas that are going to happen right when that occurs. Okay, so the outer layers will actually blow away from the collapsed core. They'll collapse and fuse, and in that energetic collision, energetic reaction explode. So these are type 2 supernovas. There's something called cosmic ray fission. This is a really kind of exotic thing, but fission means splitting. And what's happening in the upper atmosphere is a little bit of these lighter elements are formed when high energy particles from other galaxies or stars or galaxies, but maybe from other galaxies, enter the atmosphere and hit in the atmosphere. They create these small mass elements, right? These little elements. It's just a few. And then we have here, this is the brand new one, right? We'd never seen this before. 2017 was the first time, but this was created before 2017, which makes it even better. This was actually created and presented by Jennifer Johnson at Ohio State University. And what's really awesome is that this wasn't much before the event was discovered, which was kind of cool. And she actually, what's really exciting, I just learned this recently, I didn't even know this, is that she actually presented this talk at UCSB at the Kavli Institute of Theoretical Physics. This is actually where this periodic table first appeared at that talk. And then she's since improved upon it. Actually, 2008 was the original version. Okay, this is just a rough drawing. Anyways, you could read more about that if you want. But anyways, Jennifer Johnson. Okay, you're supposed to know Jennifer Johnson. Jennifer Johnson created this periodic table, and now we're like celebrating it. We love it. It's so cool. And shows how most of these heavy elements are created in the merging of neutron stars. Okay, and then human synthesis, right? There's a few elements that are only made in the laboratory because they have such short lifetimes, they can't exist in nature or survive in nature. Okay, so a couple of elements you're supposed to know. Does anybody know what AU is? AU?
Gold.
Gold. Write that down if you don't know it. AU is gold. How about AG? Anybody know AG? Anybody? Nobody took chemistry? AG is silver. Write down. AG is silver, just for fun. Silver, gold. How about PT? Anybody know PT or guess? PT?
Platinum.
Platinum. Very good. How about IR? Just for fun.
Iridium.
Iridium. That's right. Iridium. And so there's just a little bit made by dying, right? Just a little bit. But most of the gold, silver, platinum, iridium, osmium, you know, there's all kinds of elements here. How about down here? Let's go down. What's the U right down here?
Uranium.
Uranium, right? This is found inside of the Earth. But what's really crazy is look at it. All of it was created in merging neutron stars, apparently. Now, I don't know how sure they are of that. I just know that up until a few years ago, I always thought it was this that was creating most of the heavy elements, and I'm completely wrong. I admit it, I was so wrong. Okay, so the processes by which these elements get made right here. So the heavier elements have to be made kind of quickly. And so actually take a look right here. These are the processes that are found. When you make elements, there's the S process and the R process. Okay, so does anybody know what R stands for in S? S and R? They actually stand for words. Nobody knows. Okay, so R stands for rapid and S stands for slow. Okay, so the S process is found in a star that's just regular, you know, living. S, slow neutron capture, S process. It's happening in stars that are still alive, right? And they're still alive. And then the R process, rapid process, is happening when stars explode, or as we're going to learn, in the merging neutron star. Okay, so this goes into way too much detail. Wow, it's so cool though. Really, oh, look at all the fun math. We're not doing any of that. Okay, okay, so that's I guess that's it. I don't know. I don't know what else to show you guys. We don't want to. We're not going to get into. I mean, maybe we should just click. You want to click on it. Rapid nuclear astrophysics, the rapid neutron capture process, also known as the R process, is a set of nuclear reactions that is responsible for the creation of approximately half of the atomic nuclei heavier than iron. The other, okay, we didn't mention the P process, proton capture from proton-rich sources. Okay. So R process is a neutron capture, rapid neutron capture. S process is a slow neutron capture. Okay, so the speed of the neutrons and also the rate of the neutrons. Okay, so traditionally, this is what I knew, this material was ejected by a core collapse supernova, type 2 supernova, and therefore it was supernova nucleosynthesis. But anyways, so that's what I learned. And now I'm understanding that it is just not right. Okay, so then we have this kilonova, and you want to, let's see, I want to just go to the kilonova article. Okay, so you're supposed to know about this kilonova. It's a pretty big deal. And it is the very first, so let's see, a kilonova, also called a macronova. I'd never used that term, but, or R process supernova. Okay, that's interesting. This is very interesting. I did not know to call it that. But I actually maybe should tell you guys another story right now too. Actually, I have a couple of stories I can tell you about. Okay, so kilonova are thought to emit short gamma ray bursts. Should write that down. What's a gamma ray? Anybody remember gamma rays? I know we've talked about it.
Very high frequency light.
Very high frequency, the highest frequency light that we can imagine. And strong electromagnetic radiation due to radioactive decay, right? So there's these, there's these heavy elements that are unstable and that undergo radioactive decay. So it was introduced, this term was introduced in 2010, and it may have been detected by a gamma ray instrument. Yeah, actually, I think this is the first one. The first kilonova to be detected was in 2013. You guys read this, right? In June 3rd, 2013. Okay, so S, you could read this, right? I might ask you, what is this? SGRB, right? GRB, gamma ray burst. Swift, gamma ray burst, right? So actually, this is a little bit of telling you where it came from. And then observed 9 days and 30 days after the burst. Okay, so they were too late. If there was an event there that you know caused it, or sorry, that was visible, they missed it already, right? So 9 days is too late, so they didn't see anything. And then in October, well, this is a new one, right? In October 2018, they reported gamma ray burst from 2015. Oh, I'm going back here. They reported in October a gamma ray burst from 2015 that may have been analogous, but again, they did not see anything, obviously. But anyways, this is the historic one. So actually, let's just go look at that one. So this is the gamma, this is what? Gravitational wave, 1708-17. So this is the gamma ray, this is the gravitational wave, sorry. And at the same time, there was a gamma ray burst. Okay, so neutron star merger. Blah, blah, blah. Okay, artist's impression of two neutron stars. Should we see this? Illustration. Oh yeah, that's cool. I mean, you just have to understand, these are neutron stars. They are the densest material that we can imagine. And then we're going to smash two of them together, right? And so I guess I'm going to ask you to know a couple of little details about this collision. Oh yeah, that's in the video too. Okay. So anyways, a couple of details about this event. What were the masses of the original neutron stars? Okay. Anybody remember? Did I ask you that already? Anybody know the masses? There's Las Cumbres again, right? Because they had the most beautiful light curve, right? This is so cool. Anyways, they were able to see when nobody else could do it, actually. Okay, so these are different wavelengths. Okay, cool. Now I understand something. Okay, so you can see that the response is different in different parts of the spectrum. Okay, so some parts it's not even visible, right? It's just like almost not even there. Okay, here we go. Write it down. Write it down. The gravitational wave signal that was produced by the collision of two neutron stars with a total mass of 2.82 times the mass of the sun. If low spins are assumed, the total mass of the merger is 2.74 solar masses. The masses of the component stars have greater uncertainty. Okay, so we don't know, but let's go ahead and write down the 90% chance. Okay. Oh, so the larger, oh, that's not very helpful. Okay, wow, this is a big range. I don't know what question I can help you, huh? What could I say? Well, all right. 90% between these two masses. Okay, can you write it down? M1 between 1.36 and 2.26 solar masses. M2 between 8.86 and 1.36 solar mass. What? How could this be? Does anybody know why I'm having a problem with this number? Actually, even this number. Anybody? Nobody knows why I'm having a problem with it?
I feel like they're just too small.
Why?
Because wouldn't it be like a brown dwarf instead, or like a white dwarf, not quite a neutron star?
Yeah, because according to what I told you, if it's less than 1.4 solar masses, then the electron degeneracy pressure should be able to hold it up. But maybe, okay, so here's the only issue that maybe I'm wrong. Maybe I actually I should make sure that there is a difference, right? So what happens with a white dwarf is the leftover core just collapses. And so really, you know, the electron degeneracy pressure can hold it up because there's no other external force really forcing it together. But when there's a type 2 supernova, the explosion of the type 2 supernova in a way actually pushes the whole core together. So this is actually, to be honest, a pretty big misunderstanding on my part, because here we are seeing neutron star masses which are significantly less than the white dwarf masses. I have always been wrong about that. I'll admit it right now. I've always thought they were more than 1.4. And what I'm seeing right now is that professional astrophysicists are saying, sorry, dude, you can actually have less than 1.4. Okay, so I'm sorry, I didn't understand that before this moment. So anyways, but here's the key part. I can tell you that this is right. That if you take these masses and you put them together, what you're going to create is something that they claim has a mass of about 2.74. Okay, so what has a mass of 2.74 solar masses? What is it? What is it going to be? What is it? Wait a second. I thought that we saw, hold on a second. Now I'm not sure. This is very funny. Okay, there's actually another paper I don't think I've read. Oh, what the heck? I actually have been wrong. What the heck? I thought that there was a, okay. So anyways, all right, so you want to write down why this is so interesting is because 2.74 masses, 2.74 solar masses would either be the most massive neutron star that had ever been discovered or the smallest mass black hole that had ever been discovered, right? This is right on the boundary between, we don't know what it should be. We don't know. So right here is a weird thing that we've never had the capability of seeing before. We've never seen such a small mass or such a big mass. I don't know, depends on how you think about it. But the idea is that this object is a little bit of an unknown. Now, I actually read a paper that said that there was a lack of emissions coming from it, and that indicated that it was a black hole. But now, you guys might have noticed I just clicked that link, and it actually says that it has a chance of being a magnetar. So now I'm back to not knowing. Okay, sorry about that. I don't know. I just changed my lecture notes for Earth 101 to include this fact. Okay, so anyways, the neutron star merger results in a kilonova with a short gamma ray burst followed by a longer optical afterglow. So take a look at this actually. This is kind of an interesting picture. This shows you, if you notice, there are jets. I wonder if, I'll just click it. If you look at this picture, there's jets coming out of this. Does anybody know what the jets represent?
A magnetic field.
Okay, so this object, whatever it is, has an intense magnetic field. And what's generating the magnetic field? Is it the thing in the middle or the thing swirling around it? Which one is it?
Things swirling around it.
Yeah, the accretion disk around it. So some of the material is accreting around it and swirling around the whatever this is. And this is creating this intense magnetic field, which is actually partially responsible for blowing material, and also very high energy photons come out of that stream. So from this, okay, gamma ray burst, energy releases jets along the axis of rotation, forms a gamma ray burst that lasts from a few milliseconds to minutes. Okay, whoa, okay, so if it happens within several thousand light years of Earth, could disrupt the biosphere by wiping out half of the ozone layer. Okay, causing mass extinction. Okay, so we don't really want them to happen close by, but this was not very close. Actually, I don't remember. How far away was it? You guys remember? Anybody? How far away was this? Actually, I forgot. How far away? Distance. Here we go. From the okay, gravitational wave signals.
I think I said it was 130 million light years away.
Is it really that far? Wow.
But that was the galaxy that they found it in. How far?
Yeah, you know what? I think you're right. Okay. So 130, huh? Okay. Looking for, maybe it's up here, distance. Oh, here we go. So distance, yeah, there you go. 130 million light years away, 40 megaparsecs. Okay. And here's a redshift, which we still want to talk about. I need to talk about. And yeah, okay. So anyways, this is still blowing my mind because now that I'm reading this, it's changed actually from what I thought it was, but it says that either you get the smallest mass black hole or the largest mass neutron star. And it says here, a hypermassive neutron star was believed to have formed initially because of the large amount of ejecta, right? So if it was a black hole, they're claiming that you wouldn't have been able to see so much material escape. The lack of evidence, this is what I thought, for emission being powered by a neutron star spin down, which would occur for longer, suggested it collapsed into a black hole within milliseconds. Okay, so wait a second. Okay, wait a second. Did I not just read? Oh yeah, later searches did find evidence of a spin down. Okay, so this is the paper that I read, which I guess was too soon. And I should have waited, but this came out last year. So, and I did not read this before. Okay, so I don't know what to tell you. I don't know what to tell you. Maybe we should make you read the paper. You can read the paper. Huh? Can I download it? Download it. How do you download it? Oh, here. So you go to archive and then you can see the whole paper. I probably should have just read the abstract. It is often assumed that gravitational wave events resulting from the merger of stellar mass black holes are unlikely to produce electromagnetic. Yes, okay. If a tiny fraction of this gas is retained until the merger, the recoil and sudden mass loss shocks and heats it to within hours, blah, blah, blah. Whether the resulting EM emission is detectable is uncertain. Whether the resulting EM emission is detectable, uncertain. Come on, who edited this paper? The optical depth through the disk is likely to be high enough that the prompt emission consists only of photons from its optically thick skin, while the majority may take years to emerge. However, if some mechanism can release more photons, blah, 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 blah. Okay, well, this has nothing to do with, who said to go here? This, do you guys see this? Stellar mass black holes. I don't know what the heck they're talking about. Okay, so Wikipedia, I'm not happy with you right now because you got me all excited, but hold on. So, do you guys see that paper is not relevant? It's not the kilonova. Later searches did find evidence of a spin down. Well, this is actually definitely relevant. So I must have clicked the wrong thing, right? Monthly note, observational evidence for extended emission to GW. Let me just do this. Okay. And then go here. Okay. The recent LIGO event, blah, blah, blah. Okay. Sure. This association of the merger produced, this is what they're claiming, a hypermassive neutron star. Oh, what the heck? Okay. All right. Well, I went to the wrong link apparently. Okay, I don't know what to tell you guys. I was going to tell you that it made a black hole, but now I'm not sure. Oh, dang it. Okay, I'm not sure anymore. 2.0. Okay. So anyways, this is pretty cool. Wow, that's exciting. Okay, so actually now I'm really kind of excited. That's neat. That means it's not a black hole, it's a neutron star, which actually I've been saying for years that seems like the uncertainty on the neutron star mass is too confined. But anyways, I don't know. Let's take, it looks pretty technical. Okay, so I don't know what to say to you guys except that I just looking like it may be a neutron star after all. So magnetar, a magnetic pulsar, spin down, indicated by the descending chirp, may include magnetic interactions with surrounding matter from the blah, 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 blah. I don't know. Okay, this is a little bit beyond me. I need to talk to some experts. We present observational evidence from descending chirp. By frequency, it potentially indicates a magnetar. Okay, so anyways, they don't know for sure either, in other words. It could be a magnetar well below the minimum, blah, 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 about the, okay. Okay, so future observations. Okay, so I have to, okay, I don't know the answer. So I guess the answer to the question, what formed after this kilonova is not quite as determined as I thought. So you guys need to know that. Okay, so I was going to tell you today that they discovered that they found a black hole there, but that was just this paper that suggested that it was a black hole, but apparently it is not anymore. It looks like constraining the maximum mass. See, this is what I thought was super cool. Okay, so actually, can you guys write this down if you don't know what this is? Multi-messenger observations. This is a new idea in astronomy. Now that we have gravitational wave observatories, we're looking for events that generate gravitational waves and can be visible, right? This kilonova was the first one to ever show this, but they're hoping that there will be many, many more like this, right? And that means that we could use our optical telescopes, or not even optical, we can use our telescopes that detect electromagnetic waves in conjunction with, actually you could use gamma ray observatories as well, but also in conjunction with the gravitational waves to understand what's going on. Okay, so this one says, they said that they said it was a black hole. They said it was a black hole. Okay, so these two constraints actually allow us to understand that the neutron star merger, these two constraints still wow. No, I probably don't understand this. Okay, so I don't know what to tell you. Anyway, so the answer is, these guys are pretty big people though. So anyways, it looks like the answer to the question, what is there at the end of the kilonova, is not known. It is not known yet. I thought the answer was a black hole, but you could write down 2.74 solar masses may either be, actually you're writing that down, right? We don't know. We still don't know. I thought we knew. What is the 2.74 solar mass remnant of the kilonova? Should we call it G gravitational wave 170817, right? That's how you say it. Event. Okay. What is the remnant? Okay, and the answer is maybe the largest mass neutron star, or maybe smallest mass is still there. Okay, so we won't know. We don't know yet. I thought the answer was this, but now I'm not Now I'm not sure. Okay, so anyways, yeah, cool, interesting. All right, so let's see. So that's the kilonova, and it's a pretty amazing thing that it happened just a couple years ago, and we're hoping that more events like that will happen as well, and we can learn more about this. Actually, another really crazy thing to understand is how many scientific articles came out of the first gravitational wave, but also this event here. So actually, they capped the number of papers that could be associated with this particular thing, but there are seriously like hundreds of articles that were published with this data, and so every one of these events is going to be something amazing, right? And actually people can probe it in so many different ways. So one of the things that's kind of exciting is what can you do with gravitational waves? So gravitational waves experiments are actually kind of broad. It turns out there's all kinds of experiments that you can do, including one of the ones that I think is really exciting is measure the Hubble constant. Okay, so actually I'm gonna talk to you guys about the, there's an issue right now. Okay, so we want to talk a little bit about the redshift idea that we've come across before. So what does redshift mean? Anybody remember redshift? What's redshift? Redshift?
And something is moving further away from you, so it's the spectrum you see is shifted slightly more towards the red side.
Okay, so higher or lower frequency?
Higher, no, it's a lower frequency.
Right, to a lower frequency, but it's not because of the distance. What is it because of?
The speed that it's moving away from you.
That's right, because the source is moving away from you, from the observer. Okay, and so this was actually a pretty big deal that Edwin Hubble discovered, and I think I've already talked about this a little bit, but Edwin Hubble discovered that other than the local group, anybody know what the local group is? And actually, I just looked this up the other day. I didn't know this. There's about 30 galaxies in the local group. What are the local group? They are the nearby galaxies, the Milky Way and other nearby galaxies. In fact, let's see if I can just quickly local group.
I know at least 4 of them, I think.
Oh yeah, what are they?
So us, the Milky Way, our 2 closest neighbors, the small and large Magellanic Clouds.
Very good. Okay.
And Andromeda.
Andromeda. Very good. Okay. So there's actually, if you look, there's just a handful of galaxies. And why, Lonnie? Why is Andromeda so interesting? You guys, you know this.
Oh, it's coming straight for us.
Okay, so Andromeda is on its way towards the Milky Way, and one day Andromeda and Milky Way will merge into a single galaxy. Actually, so that's actually a pretty. This is worth just a few seconds of your time. Milky Way merger. It's going to take a while. Let's see when we know this. Okay, video. Oh, let's watch a video. It's funny that it's a video. Here we go. Simulation. That's fine. Okay. The preview. Okay. Spoiler alert. What the heck is this? What is that? That's a weird idea. Okay. So spoiler alert, the Milky Way is going to die one day. Okay. Spoiler alert, the Andromeda Galaxy is going to die one day. Well, of course, everything's going to die. But here's the crazy thing is that they are eventually going to merge together. So you can look in the lower right-hand corner, you can see the time passing. We're talking about billions of years from now. Hey, there's another one, Triangulum, kind of drifting away. But Triangulum is gravitationally connected too. All of the local group is gravitationally connected. You'll notice that actually both galaxies are going to be affected as they get close to each other. And they're going to, well, now they're obviously affected. They're going to cause each other to be disrupted. They're going to stretch their bodies and with tidal forces. And then you'll see something very interesting. You'll see them eventually merge, okay? Now, here's an important part. When they collide, how many stars do you think we're going to smash into each other during the collision?
Maybe 3.
Is that right? 3? Okay, but pretty much none. Okay, of the billions of stars in the Milky Way and the trillion stars in the Andromeda Galaxy, there's so much space between stars that they basically are not going to hit each other. But this merger is going to be the merger of the stars. They're just going to go together, and they won't be a spiral galaxy anymore, which is kind of a fun thing to understand. They're going to be what's called an elliptical galaxy. But anyways, other than the local group, which includes Milky Way and Andromeda, all the other galaxies are receding. Okay, and so this was a pretty big deal, right? Why would it be that everybody's receding? And the answer is, well, because the universe is expanding, right? Universe is expanding. Okay, we've been talking about this for the whole course. And so Hubble came up with a law, right? Hubble's law. I put law in quotes because obviously it's not a law. It's a relationship that he certainly doesn't understand it, although he gives a kind of an explanation, right? The explanation is kind of like if you take a small balloon and then inflate it, right, to make a bigger balloon. The spaces between two objects that are close together are going to grow correspondingly, but the further apart things are, the greater that distance will grow, right? So the distance between adjacent stars will grow, but if you're going diagonal, the further away you are, the greater that space will grow. The faster it will tend to grow away from each other. So each one of these is supposed to be a galaxy. I'm not going to draw the whole thing, but okay, these are supposed to be galaxies moving away from each other. So anyways, here's the law. He said that the speed, the recessional speed of a galaxy or an object equals this Hubble constant times the distance. So the greater the distance, the greater the speed. It's directly proportional, right? Distance to the galaxy. This is the Hubble constant. Okay, this is the recessional speed. I already showed you that. Okay. All right. So now, you're kind of like, well, how does this work? Well, you need to know something. Actually, this is probably the only math in the whole final, huh? Right here. I'm about to do it with you. The distance is measured in megaparsecs, right? Which means millions, 10 to the 6th parsecs. If you forgot what a parsec is, it's 3.26 light years. Okay. And again, we're not going to worry too much about math. I mean, it's going to be very simple math. Okay. So what is the value for the Hubble constant? Well, here's an interesting story. It's been changing. And the Hubble constant is supposed to be a constant, but as our observational capability increases, technology increases, and we observe more and more of the universe, the value has been changing over the years, and I've seen it change a number of times. And this Hubble constant is basically kind of trying to tell us about how the universe is expanding. What is the rate at which the universe is expanding? So anyways, let's actually see if we can just find actually the value right now. Let's find the value. So go to Wikipedia, because Wikipedia has everything. And we're going to look up the Hubble constant. Okay, Hubble's law. Okay, Hubble law, Hubble constant. Okay, Hubble's law. And you can see right here, the Hubble law. Okay, Hubble's law, B equals HD, H0, I guess. Okay, sorry. He originally calculated the value, blah, blah, blah. Okay, so it's his value is about 70. You can write that down right now. The value is about 70. Okay, so the value currently is about 70. So we'll call it, actually, he put H0. Let's put a 0 there. H0, 70. And you want to make sure you write this down. Kilometers per second per megaparsec. So how does that work, right? Well, this is based on the expansion of the universe. The further away you go, the faster the objects will be moving relative to us. So as an example, let's try to put in, some number here. Let's put in 100. Okay, let's put a distance of 100 megaparsecs. Okay, then let's use the formula. So V equals 70 kilometers per second per megaparsec times 100 megaparsecs, and that cancels the megaparsec. And so you get 70 times 100, 7,000 kilometers per second. So that is the recessional velocity of a galaxy, which is 100 megaparsecs from us. So is a megaparsec, what's a megaparsec? Well, just so you know, the distance to Andromeda is anybody know? 2.5 megaparsecs approximately. Okay, about 2.5, right? So 100 megaparsecs. So anybody who's kind of close to us is not going to be receding. This effect is only seen when you go outside of our local group. So you need to have a pretty big number here. It's got to be pretty big. So now the reality is that we see galaxies which are gigaparsecs, right? What does that mean? That's a billion parsecs away, right? And so you just want to understand, what does that mean? What's a giga? It's a billion, okay? So now you got to do this times a billion. What's that, 10 to the 9th? 10 to the 9th parsecs? Or actually, what would it be? 10 to the 3rd megaparsecs, right? A billion parsecs, 3 billion. Am I doing this right? Okay. Anyway, so now what's the speed of something that's this far? And the answer is 70 kilometers per second per megaparsec times 10 to the 3rd. Sometimes I'm doing something wrong. What am I doing wrong? How far? Okay, anyways, we'll get back to it. And what do you get? You get 7 times 10 to the 4th. Oh, okay, never mind. Kilometers per second, kilometers per second. So what would this be in meters per second, just so we understand? What would that be? Well, kilometer is 10 to the 3rd. This is 7 times 10 to the 7th meters per second. So does anybody notice something about the speed? Is it the speed of light yet?
It's 1 magnitude short.
Yeah, it's 1 magnitude. Actually, well, it's about 10 to the 8th, right? That's actually the same order of magnitude as the speed of light.
Oh yeah, rounded up just
It's about 1/4 the speed of light, actually, right? It's about 0.25 C, just so you understand. So now this formula right here that we've been working with, right? This formula, right? What would happen if you put in a bigger and bigger d? Wouldn't this eventually go faster than the speed of light?
Yeah.
Of course, right? If you put in a big enough d, it turns out that you can actually go faster than the speed of light. Now you might feel like, so what if I put in, let's say I put in 10, that's too much. How about 3, actually even, yeah, 3. That's too much. I can't go that far. All right, actually, just never mind. With big enough d, V is greater than, not greater, not much greater than C, just greater than C, not much greater than C. And this is allowed, right? This is allowed because it's not special relativity, right? Because it's not special relativity, right? The expansion of the universe is governed by what version of relativity? The expansion of the universe, the expansion of space-time, the acceleration that we see, this is general relativity. And it does not care about the speed of light being a maximum speed. That's not the case. So relative to each other, two galaxies can actually be moving relative to each other faster than the speed of light. That's okay. So in fact, let's say I'm moving at 1.4 C, right here. This is where we live, Milky Way. We're thinking about the big distances, right? And you eventually get to a distance where this galaxy is moving with a speed of 1.4 C. We have this new idea here, which is actually kind of like Mach number. Like, have you guys heard of Mach number? Anybody heard
I
of
think I've
Mach?
heard the speed of sound referred to.
Right, this is times the speed of sound. Right, so if you go Mach 2, right, 2 times the speed of sound. And for those of you cartoon fans, Mach 5, right, 5 times the speed of sound. Anybody know Speed Racer? Okay, all right. Anyway, so Mach 5, right? So what's the corresponding? It's like Mach 5 number, so it's called the Z number. Okay, the Z number is the ratio of the velocity to the speed of light. And so for the above example, 1.4 C divided by C, right? We just get a Z number of 1.4. So you can see anything Z greater than 1 is faster than C. And so you're going to learn that that this is possible. Now, I actually have not looked this up in a while, and so I'm gonna remind myself what it is. But one of the exciting things is a few years ago, there was an announcement of the most distant galaxy. Right? Did anybody hear about this? The most distant galaxy, most distant galaxy ever detected, ever seen, right? It was using Hubble, most distant galaxy. And the part that's really exciting is imagine what happens because of this speed. What happens to the light as a result of this speed? We said it before. What's the name that we give? This is also known as the redshift. Sorry, I should have told this redshift, okay? Okay, the redshift Z is actually going to tell us about what has happened to the light, okay? So what happens to the color of the light when it's far away? What happens?
It gets redshifted.
It gets redshifted, right? So what color is a galaxy right now when we look at a galaxy? What color do you see? Can you see it in the visible part of the spectrum? Is a galaxy visible?
And they're very faint, but they're certainly visible. You can.
Of course they are, right? If you could see one with a telescope, then it has an optical element. Now, it may also emit light in other parts that we don't, that we're not aware of. But one of the things we're sure of is that because there are living stars there and they emit light that we can see, then they are visible. But here's the part that you want to understand. This most distant galaxy had no visible light. And I'm using the word visible to refer to the visible part of the spectrum. So what color light do you think it might have been? Not visible.
Infrareds?
Infrared. So this one was shifted so far that none of the visible light was there anymore. It was shifted into the infrared, okay? So we're about to find out the Z number, Okay, and I want you to be able to write this in your notes. Okay, so let's see what the answer is. I don't know what it is. I forgot. I know I've read it at least once, but I forgot now. But let's look it up now. Here we go. Let's see. Most. I'm going to ask Wikipedia first, so I don't have to waste my time going out on the internet when Wikipedia has it. The most distant galaxy does not exist. Shoot. Most distant galaxies. Most of blah blah blah. List of galaxies? No. List of galaxies. Okay, list of galaxies. There. What? I said 30, 51. I can't believe how I just looked this up. Are you joking? I looked in the wrong place. Oh, darn it. I was told 30. I was told 30. There's 51. Oh my God, I love that. That's great. Okay, list of galaxies. La la la. This is taking too long. Okay. Oh, look at this. Just so you know. Z number 6.604. Just so you know, right? Okay, I can't find it. Okay, hold on. Most distant. Oh, here we go. Closest and most distant known galaxies by type. Okay, here it is. Most distant galaxy, write it down. An estimated distance of 32 billion light years, co-moving distance, or 13.4 gigalight years light travel distance, because it basically, the light that we're saying left at the beginning, near the beginning of the universe, and it has a Z, write it down, of 11. Okay, so we are looking at something that from our point of view appears to be moving away from us, or should be moving away from us at this point, at 11 times the speed of light. Okay, which is kind of bigger than I remembered. I was thinking something like 3, 4, but look at that, 11.09. Okay, the most distant galaxy. So actually, we only have a couple more minutes, so let me just click on this just to see. Is a high redshift galaxy found in the constellation Ursa Major. The discovery was blah blah blah, 32 million. The galaxy was identified by a team studying data from the Hubble Space Telescope Near Infrared Deep Extragalactic Legacy. Okay, a survey. Okay, and Spitzer. Okay, blah blah blah. Okay, and is observed very close to the end of the so-called dark ages and near the very beginning of the reionization area. Okay. Okay, was forming new stars approximately 20 times. Okay, so the age of this galaxy currently, as we see it, is 40 million years old, right? So there's lots of new young stars there. The fact that a galaxy so massive existed so soon after the first star started to form is a challenge to some theoretical models. Okay, so it's a little bit too organized. I wish I could see the redshift. Well, anyways, it's infrared. Okay, it's infrared. So it's not a visible image. How do I see that? I can't see it. Where? Okay. Maybe this article. I like National Geographic, but I don't see it. Do you? No. Let's try this one. Oh, this one. NASA. Okay. Ooh, should we watch the video for a final thing? Let's see. Animation. Okay, sure. Let's watch it. Why not? 33 seconds. Everybody recognize the Big Dipper? That looks visible to me, if I can see it. Huh. Okay, well, now I'm a little confused because I just told you it was infrared, but no, I'm not sure because that was a visible thing that we just saw. So blah blah blah. Unless that was an infrared picture, that could be. Oh, it is. Okay, thank goodness. Okay. This discovery has, no, it doesn't say that. This is W first. Okay. We need a data. We need the actual data. We need to look at that. G and Z11. I think it's shifted into the infrared. Actually, I mean, this seems to be stretched to longer. Okay. Oh, well, I don't know. This seems to have an optical element. I might be wrong. I said it was only infrared, but clearly there's something visible there. So I may be wrong about that. I think that they detected, this seems to be the shift of Z equal 11 is actually a pretty large shift. I thought that would be, okay, I might be wrong. I guess I'm wrong. Oh, hold on. Expand, blah, 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 okay. We need spectroscopy. Okay, so I guess there is still some visible light. Objects located at great distance may have their spectral lines shift the presence of light. Okay, we need spectroscopic information. So it's very redshifted, but apparently still has a visible element. So I'm actually wrong. I think maybe most of it is infrared, but obviously some of it is still visible because you can see it. But then again, you could think about some of the higher energy photons could be shifted and maybe they are visible. Maybe I'm just missing the main peak is infrared. How about that? Does that sound reasonable? I'm pretty sure that's right. But it does have some visible element because if you shift a very high frequency down by the same amount, you still get into a visible. That seems reasonable. What do you guys think? I'm thinking that might be it. Okay, so I didn't get too much beyond this. This is something I wanted to do, the redshift, and I guess I will, there is something I didn't get to though today. And so I think what I'll do is I will include along with your questions today, I'm gonna ask you to read a little bit more because we have a little problem today when you ask how do you get the best value for the Hubble constant? How do you get the best value? It turns out that we will eventually use gravitational waves, right? But there are two competing techniques, right? There's two competing techniques. And which one's better? Well, they both have their people that believe in them. But actually it's the Hubble constant, so it doesn't matter, right? So with whichever of the techniques, you're getting the right value, except something has happened in the last couple of years. These two techniques don't give the same value for the Hubble constant. They give two competing techniques and they have two distinct values for H0. Now, it may be that somebody's wrong, right? One of the groups is wrong, but they have a lot of confidence in what they're doing. And so I will tell you that there's another solution, and actually we'll talk about that next time. But maybe what I'll ask you to do is to at least understand a little bit more, what does this mean, right? The value of the Hubble constant is how we calculate the age of the universe. So every time we change this value, guess what? We change the age of the universe, not because it's really changed, but because when we calculate the age of the universe, we use this value to work backwards, kind of like the way the Crab Nebula was established in year 1054 by looking at the expanding cloud. So the expansion of the universe, work it backwards, gives you the beginning of the universe. Okay. So I think that's about it for today. Anybody have questions? Want to ask questions before we leave? But basically, I'll ask you guys some questions for your participation, and then I'll ask you to read a little bit about the two competing mechanisms or methods, right? Methods for generating the Hubble constant right now, and to understand that they're different. Question, Lonnie?
Yeah, I had a question about the participation quiz for last week.
Uh-huh.
It said that to list what laws you expect merging black holes to follow. And I definitely knew that it conserves conservation of angular momentum and energy. And then when it said I got it partially right, I was like, okay, well, charge makes sense to me too. But I didn't quite understand how they keep conservation of linear momentum. It said that was right as well.
So what is linear momentum? Yeah, actually, so yeah, that's just, okay, so yeah, don't feel bad if you got that wrong. But linear momentum says that, so here's the problem, right? So we know that when the black holes merge, right, that some of the matter is going to go into making gravitational waves. But if you study a system and things are moving, right, they have a velocity, mass, velocity, m1, v1, 2, v2, right? Whatever it happens to be, the cumulative motion in some direction is called linear momentum. So suppose that, we're talking about two black holes merging, right? These are merging black holes, and they're going to form one, but they're not actually standing still, right? If you watch the center of mass, it's moving away from us with some speed, okay? And so the cumulative momentum of that system has to remain the same when you're done, okay? So even if the gravitational waves eject mass, the overall momentum of the system must still be there. Now, so actually, in fact, I don't know, I'm not an expert at gravitational waves, but the gravitational waves may not be radiated uniformly in every direction. And if that's the case, then you may have to worry about the momentum that's actually imparted to the gravitational waves. But I would guess that it's somewhat symmetric. That's just my guess, okay? And as a result of that, we're going to find out that the original momentum that was in the system before has to still be there. So in addition to, so these are basically the conservation laws that we always have, right? The conservation laws that you should always be aware of if you're doing problems on the Earth would be conservation of energy, conservation of linear momentum, that's P, right? Mass times velocity. Conservation of angular momentum. That's going to be capital L. Conservation of mass, right? Because that's usually the case. Conservation of mass, conservation of charge, right? All of these are typically true for you and me, because we don't have to worry about matter just disappearing. But in a black hole, this is the only one that can significantly change, right? Because it's going to be radiated as the gravitational waves. The rest of these things must still be true, in other words. So that was kind of a little trick. I wouldn't worry about it. It's not going to be a big deal. But just be aware that the mass changing cannot actually change the overall momentum of the system.
All right, sure.
I mean, unless I could be wrong, by the way. If you can find evidence of that, by the way, that would be awesome. If you could find evidence of momentum being transferred to the gravitational wave, then it would still be true, but we wouldn't see it anymore, in other words. Okay, all right, so thank you. All right, so we'll see you guys on Wednesday. Thank you so much. Have a great day.
Yep, you too, Professor. Thanks.
All right, bye.